last day today. I've put together a revision lecture where I have too many slides, but I'll try. And all of them have a little circle at the top right corner that tells you exactly what lecture that slide is coming from. Okay? And I've organized it so that first we have igneous and second we have metamorphic. Whereas in the course we've been kind of cycling in the dynamic earth, because my goal was for you to understand how everything's really interconnected, and we really have a very interesting element cycle. We are recycling our chemical elements all along the way. But today, to make it a bit different and maybe have a different insight, that's why I decided to go igneous first and metamorphic second. For the exam, obviously you have to go through everything. This is not comprehensive enough. You are encouraged to check the textbook, which is really good, and to ask questions, okay? Please come and ask questions. I'm there to help, hopefully. Yeah. So I think that's it. And in the lectures, in all of them, I always had a summary slide at the end, so that's kind of like a summary of each of the lectures, so I hope that helps as well. So for the revision lecture, we're going to, as I said, we're going to start in the mantle, then go igneous, and finally metamorphic. So if you remember from lecture 4, the mantle is normally solid, because this is a phase diagram, temperature versus pressure, where we can see that how the conductive geotherm, which kinks in the limit between the lithosphere and the asthenosphere, is always to the left of the solidus. So if we want to melt our mantle, we have to cross the solidus line, either by reducing the pressure, increasing the temperature, or moving the solidus to the left. But if that doesn't happen, we are solid. And mantle rocks, as you've seen, or at least you've seen the upper mantle rocks, have a very simple mineralogy. Yeah? So you normally get olivine, CPX, and OPX, and those are the three minerals you use to classify them, plus an aluminium phase. Yeah? And the key thing, or the interesting bit, is that the aluminium phase is pressure dependent. Yeah? So if you have garnet, it means you are at a pressure of about, a depth, of about 60 kilometers or more. If you have chromium spinel, you're at lower pressure in the mantle, and if you have plagioclase, you are even lower pressure, below 20 kilometers depth. Okay, so it's quite interesting to recognize which aluminium phase we have in a mantle rock, because we know where the mantle rock comes from. And we also saw that, okay, we classify them disregarding the aluminium phase because it changes. We consider olivine, CPX, OPX, but most of our rocks are lerezolites, so something that falls kind of in the middle, that has a bit of everything, yeah? So in this classification diagram, everything that has olivine over 40% is a periodite, so most mantle rocks are periodite, and normally they are lerezolites, but we also have harzburgites. What are harzburgites? What are they related to? What happens if we extract melt from a lerezolite? We're going to extract a basalt, which we will see in a minute. It's going to plot somewhere here. So if we extract basalt from lerezolite, the residue becomes harzburgite. Yep. That's why those are the two most important rocks in the upper mantle. And this, for example, would be a garnet lerezolite, because we don't use the aluminium phase to classify the rock, we kind of add the description when we give the rock name. So what happens when we manage to partially melt the mantle? We were not going to be able to completely melt it, but partially melt it. What happens? Well, we start with a lerezolite, something that has a bit of everything, CPX, OPX, olivine. And that's the rock you have on the left-hand side, okay? If we start melting, if we start increasing the temperature, we're going to start melting at the first point where we get some sort of melt. What point is that in a ternary diagram with like the one you have on the right-hand side. Yes, the eutectic. It's going to be the first point, but we're going to actually be able to melt something, okay? And because that eutectic point is quite close to CPX, which is at the top of the diagram, that's why basaltic rocks or basaltic melts have a composition which is different from the original one, which normally is going to be a lersolite, yeah? So we start with the red dot, we obtain a partial melt, which is the E-blue dot, and as a result, we get a residue which is progressively depleted in that, okay? And it's going to be moving in the opposite direction, okay? And a mantle rock that has lots of olivine here and OPX and no CPX left is called Harzburgite, yeah? If we were able to continue melting, which is quite difficult, we would actually consume all the CPX. And if that happens, we can no longer sit in the eutectic. We have to move along the cotectic line in this direction, where we only have OPX and olivine, yeah? And as we do so, the melt we are extracting is changing in composition. And as a result, the residue is also changing in composition from a Harzburgite to eventually a rock, a periotite, which is purely composed of olivine. How do we call that? Dunite, yeah? So dunite would be a residue of further melt extraction from the mantle, okay? So we start with lersolite, take CPX from it, convert into Harzburgite. If we even take more from it and even the OPX as well, we end up with a dunite. And the melt that we get is the basalt, but the basalt is changing in composition if we are changing the rate at which we melt the mantle. Yeah? So this was the answer to the question. If we remove blue basalt from red lersolite, we end up with a residue which is called Harzburgite. If we continue melting and remove all the OPX as well, we will end up having a dunite, which is up here. And this explains also why lersolite, which is the original mantle rock, and basalt, which is the partial melt, are different in composition. So in a basalt, we have much less magnesium than in a lersolite. Yes. Yeah? And as a result, basalt is mafic and not ultramafic. We have more than 10% of felsic minerals in a basalt because we have less magnesium in it. And we also have more aluminium and more calcium than in the original Ceres rock, in the lersolite. And very interesting, we also have more of sodium and potassium than in the original lersolite. How do we call these two chemical elements together? Total alkalis, yeah? We're going to use them later to use the task diagram, yeah? So remember, keep this in mind. Basalt not only has less magnesium and more aluminum and calcium, also more alkalis than lersolite. And as I was saying, when we are partially melting our mantle, depending on how much we actually melt it, depending on the melt fraction, we're going to have a different basalt. Always a basalt, but a basalt with a different geochemical affinity. That also depends on temperature and pressure, but melt fraction is really, really important. And we've learned that we have low degrees of partial melting of our mantle. We're going to favor having alkali basalts, yeah? Because this is how the mantle looks. We have that the mantle is heterogeneous. We have the main dough of this cookie dough is lersolite. But we also, remember, have raisins, which are the recycled slabs, yeah? When we have subduction and we eventually subduct our slab into the mantle and that subducted slab gets recycled, we are adding basalt. So a subducted slab is nothing else but metamorphosed basalt, eclogite. We are adding that component to a mantle, making it more and more heterogeneous throughout geological time. And the interesting thing is that when we melt our cookie dough, the raisins or the recycled slabs or the basalt melt first. So when we have alkaline basalts, we are preferentially melting the raisins. If we increase our melting rate, we might be able to also melt the rest of the leusolite. Okay? So the mantle is solid, and it is also heterogeneous. And because we are partially melting a heterogeneous source, we get a broad range of compositions in our produced partial melts or basalts. Yeah? As we saw, there were 3 different ways of melting the mantle. Yeah? First one, mid-ocean ridges, decompression melting. Very interesting, up to 20 to 30% partial melts. Really high degrees of partial melting in this setting. What is the basalt we get? Mid-ocean ridge basalts are tholeiitic. Yeah? Second option, wet melting. Above a subduction zone, we are releasing the water by metamorphosing a basalt. And the water enables us to move the solidus to the left and have partial melting. The amount of partial melting we have will depend on the availability of water. But the beauty of this second option is that we are generating volcanic arcs on top of the subducting slab, generating a beautiful arc where the affinity or geochemistry is calcalkaline because we have lots of crustal input. It's going to be very easy that we get crustal contamination. Last option, we increase the geotherm towards higher temperatures. And we also heat the solidus, in which case we can also get partial melting. But you can see that at least at the beginning, the rate of melting is really low, only up to 5%. As a result, we get alkali basalts. We're only melting the raisins, yep, which have lots of sodium plus potassium, therefore lots of total alkalis. Therefore, we get alkali basalts. We might have this plume going on for a long time if the plume is, successful and starts generating rifting, so the lithosphere on top of it starts to break apart. And if we do that, we might eventually produce, stretch the lithosphere and produce upwelling of the asthenosphere in between and eventually produce new oceanic crust. And oceanic crust is tholeite. So if we increase the melting rate, we can go from alkaline to tholeiitic basalt with time. Yeah? And that's when we get, and related to this hotspot melting is when we get large igneous provinces or lips, including Hawaii, including the Afar plume here, or the Cameroon line, including the Australian. They don't have the continental one, but they have the seamounts here. So all of these large igneous provinces are initially generated by an upwelling plume, which eventually separates the lithosphere apart. Yeah?
When the Deccan and Siberian traps, what type of volcano made those? Because they're massive, big deposits.
Yeah, and it's beautiful because in the Deccan traps in India, you have really alkaline rocks. So again, it's hotspot melting.
Is that for Siberian as well?
Yes. Yes. So what we get is different depending on the melting rate. In mid-ocean ridges, we get mid-ocean ridge basalts, so morbs, which are always tholeiitic. By contrast, in plume settings or hotspot settings, we get OIBs, OIB-type magmas, ocean island basalt, which can eventually be tholeiitic, but they're going to be mainly alkaline. And this links us to the task diagrams, where we have total alkalis versus silica. And therefore, if we are high in total alkalis, we are alkaline above the black bold line. If we have less total alkalis, we are subalkaline. And there are 3 different differentiation trends: silica undersaturated, silica saturated, or silica oversaturated, depending on the amount of silica in our melt. Yeah? And we get to know that by knowing the chemical composition of a rock, knowing the normative mineralogy. So a bit more in detail, remember we never can have nepheline and quartz together because there's a thermal divide in between, okay? And this is marked by the normative mineralogy, which also again separates our fields of silica under saturation, saturation or oversaturation. We basically have nepheline on the left-hand side here, quartz on the right-hand side here, and a thermal dividing line. And we have alkaline to the left and subalkaline to the right, but we can divide the subalkaline, as we've seen, into calcalkaline or tholeiitic, depending basically on the iron content. Now be very careful with the diagram, the AFM, which is not similar to the ACF in metamorphic rocks, and that's a bit confusing. So check what the three end members are in each of them and what they mean in the two different environments. So those are the three affinities or geochemistries of basalts, which are completely related to the way we are melting our source. And that is completely related to the geodynamic setting. If we are in a subduction zone, if we are in a mid-ocean ridge, if we are in a hotspot. Yeah? So by knowing the composition of a basalt, we can get to know how the mantle melted. And the three types of basalt, alkaline and subalkaline, which divides into tholeiitic and calcalkaline, tells us a lot about geodynamic setting. Yeah? We also saw that we could see that in terms of trace elements. This is a rare earth element diagram normalized to chondrite with increasing incompatibility, remember, to the left. This is exactly what we saw in the paper discussion, but we saw it a bit more complex because we had extra elements. But in a rare earth element diagram with just the rare earths compared to chondrite, we would, if we were going to melt our mantle completely, we would be in the one line. We would be melting the whole lertholite. But as we decrease the melting rate, what we're doing is increasing the amount of incompatible elements in the melt, because those like the melt, and so the less we melt, the more that melt is going to be enriched in incompatible elements. Okay? Again, these incompatible elements would come out, especially if we only melt the racins of the heterogeneous mantle. And this is why mid-ocean ridges, which have quite high degrees of partial melting, are relatively flat, whereas OIBs related to hotspot melting, where the melting rate is lower, are more plungy. Yeah? So geochemistry was quite good in two senses. First, to know more about how the source has melted, how the mantle melted, and second, to know about how the basalt we produced differentiated, if there was any kind of processes of magma differentiation. So we have our mantle-derived magmas, and they have like a journey to the surface where they can get stuck at different levels and different reservoirs. So we might get plutonic rocks, which are phaneritic, if the magma crystallizes slowly at depth, or volcanic rock, which are aphanitic, if at least part of that magma crystallizes quickly at the surface. Okay, so texture tells us about the way the melt that basalt has crystallized. And so the way it has crystallized depends on many different things, but we learned that mostly it's going to depend on pressure, temperature, and composition. And to get to know more or understand better how this actually works is when we started working on phase diagrams again. Yeah, where we have temperature, in this case it's kind of in the third dimension, and we have composition in three different axes, and we are assuming a constant pressure for each of these phase diagrams. So depending on where we start, depending on the composition of our system as a whole, we will have different crystallization paths. Yeah? So, for example, if our rock has an amount of plagioclase, pyroxene, and olivine that it plots in the X location, as we decrease the temperature, we're going to start crystallizing olivine, yeah? Because we are in this first, right, crystallizes first field. When you look at phase diagrams, remember, it's the same idea for mantle melting and for magma crystallization, but we're looking at the diagrams in the opposite way. If we are melting, we are increasing the temperature. If we are crystallizing, we are decreasing the temperature. Yep. And the minerals we use in the different diagrams depend on the composition of the system we have. So in a basalt, it's likely that we have plagioclase, pyroxene, and olivine. If we don't have olivine, well, we can use a simpler diagram with only pyroxene and plagioclase, which would be this one here. This is a binary phase diagram. Okay? So imagine we are in X and we decrease the temperature so that we start crystallizing olivine. And as we crystallize olivine, if we extract olivine from that melt, again, the melt has to forcefully change in composition accordingly. We are depleting our melt in this end member, and as a result, our melt is going to evolve in the opposite direction, yeah? Until it hits the catectic, where diopside starts crystallizing as well. And we decrease the temperature along this line until we reach the eutectic, where all the three minerals crystallize together. And we will not be able to change the temperature below 1270 until all the liquid is consumed. Because below that point, there's no liquid in the phase diagram. Okay? So this is the ideal crystallization path of magma with composition of X as we decrease the temperature. What could happen is that we start crystallization at depth in a chamber, and at some point we have that the melt is extracted as a volcanic eruption, in which case we will have to see which are the phenocrysts that crystallize at depth and what are the microcrysts that crystallize at the surface. And maybe we are not able to see the whole path, because if we have a glassy ground mass or a very, very fine-grained ground mass, we will not be able to see what happened after eruption. Okay? And in any case, when we are looking at igneous rocks, we are looking at minerals and texture. So the texture, as I just said, depends on the way we crystallize the magma, depth or surface, aphanitic or phaneritic, sorry. The minerals will depend on the composition of the magma. So all these magmas start being basalts if they come from the mantle. And we might have a process by which the basalt changes into a more intermediate melt, such as andesite, or even more felsic, such as rhyolite. And this process of going from a mafic rock to an intermediate to a felsic one, we call magma differentiation. Yeah? If we start in the mantle, necessarily we get a basalt. Yeah? So we need some sort of mechanism to move along that line. And depending on the composition of our magma that we get, mafic, intermediate, or felsic, we'll have a different mineral assemblage. Okay? We will not have quartz in a basalt, probably, and we will not have olivine in a rhyolite. Yeah? And we looked at 4 different mechanisms of magma differentiation. Fractional crystallization, magma mixing, assimilation of country rock, and partial melting of the crust. Okay? In fractional crystallization, we go from mafic to intermediate to felsic. In mixing, we mix 2 end members and get a hybrid. And when we assimilate country rock, we will change the melt composition towards whatever we are assimilating. And when we partially melt the crust, we get a felsic melt. Yeah? And this is what we just saw in the migmatites. And we know about these processes because we now understand much better plumbing systems of volcanoes, including the plutonic area and the volcanic area. And this actually didn't say when I showed it to you before, but this is from Mount Yasur, that's Vanuatu, that's next door. Okay? So we look at plutonic and subvolcanic intrusions, and we look at volcanic products and the minerals or phenocrysts they contain. Okay? And in this case, for example, we saw that this particular plagioclase crystal with low birefringence is nicely zoned with oscillatory zoning, and then it kind of gets broken and is overgrown by new layers, by new zones at the end, yeah? So we would have to see if the chemistry of this plagioclase from the core to the rim changes and how it changes, yeah? So if these bands here are related to fractional crystallization, you would expect what sort of change in composition? Yes. If then you have some resorption, what sort of process would you interpret? Magma mixing, and then we also have some layers here. So if the layers go again from calcium to sodium is further fractionation. If they go from sodium to calcium is further mixing with a more mafic melt. Okay? So it's about reading what kind of processes we can get at the mineral scale and also at the whole rock scale. We learn to recognize mixing fractionation using whole rock compositions. Remember? When you were fractionating minerals from a melt, you were changing the composition of the melt accordingly along a liquid line of descent. So if these white dots are different volcanic rocks, how would you know which one is more mafic? The one with highest magnesium would be the most mafic one. If they are all related by fractional crystallization, we would be expecting lower magnesium with time and higher titanium if what we are extracting is a combination of OPX and olivine. Yeah? This process of fractionation we can also see from the trace elements. For example, if europium is a trace element particularly enriched in plagioclase with high partition coefficients in plagioclase, if we extract plagioclase from a melt, the residual melt will have a bump in europium because we are extracting plagioclase which has lots of europium from the melt, and as a result the melt gets depleted in it. Yeah? So the geochemistry tells us a lot about the way we melt the mantle if the rock comes from the mantle, but also about differentiation process, in this case fractionation of plagioclase. Yeah? And so we've been looking at generating melts from the mantle and then differentiating them. And as we differentiate them, we are changing the silica content. As a result, if we are increasing the silica content, we are increasing the viscosity and therefore the gas saturation. And if we do that, we might end up with an explosive eruption. Again, it's not the same opening a bottle of Hawaiian red wine than opening a bottle of rhyolitic champagne. Yeah? Gas saturated, very viscous and explosive. What happens with the magma is if we open a bottle of Hawaiian red wine, it goes down and we have a lava flow. Yeah? If we have a rhyolite and we open the bottle of champagne and it gets fragmented into pieces of rhyolite, we get a pyroclastic deposit. Okay? So the type of volcanic eruption controls the type of product and also the type of edifice. Yeah? So the biggest volcanoes in terms of aerial extension are shield volcanoes, the Hawaiian ones, because lava, basaltic lava can run a lot because it's very low in viscosity. And as we start getting more viscous felsic magmas, we start getting taller volcanoes. So for example, stratovolcanoes like Fuji or Santorini, or even large calderas, because we have had a massive explosion related to the collapse of the volcano on top of the emptied magma chamber. Yeah? So the more felsic, the more viscous, the more gas saturated, the more explosive, the more fragmented, the more dangerous. As we can see from the example of Mount Vesuvius, or for example Mount San Helens or Mount Pinatubo closer to here. Yeah? When we have explosive eruptions, we first have an eruptive column, and an umbrella region which generates fallout products. And when the plume gets denser than the air, and when we lose a bit of the initial energy and collapses, we get the very, very dangerous pyroclastic density currents that, when they come to rest, generate a pyroclastic deposit called ignimbrite. Yeah? And those ignimbrites may undergo welding if they're hot enough. Okay? So these ignimbrites are just basically pieces of this fragmented magma, for example, pumice or scoria or sputter, mixed with pieces of lithic fragments, so pieces coming out from the conduit, for example, and that all goes to rest all of a sudden, and if it's hot enough, it might weld together. So the pumice fragments, which look very light and vesicular, can become fiamme when they get completely compacted. The glass shards, which are really nicely shaped here, in between gas bubbles, you can imagine one bubble there, and one bubble there, can become completely compacted and very, very glassy. Yeah? And this happens when we have a pyroclastic deposit, which doesn't look like a lava flow at all. It looks more like a sandstone, to be honest. You know, it's a granular deposit. It's composed of pieces of magma, fragmented, because it's been erupted in an explosive manner rather than an effusive manner. Yeah? And it all relates to magma composition. So from mafic to felsic, we can undergo magma fractionation, but there is, we would need loads of basalt to produce granite, 41 parts to 1, because granite and basalt are really, really different in composition. And we saw that the fourth mechanism is more efficient in producing granite. What was the fourth mechanism of magma differentiation? Crustal melting. So rather than undergoing differentiation from basalt into rhyolite or granite, if we melt the crust, we are much more efficient in generating felsic melts. Okay? And this is going to happen particularly if we have a thick continental crust, where it's much easier. In a thick continental crust, it's much easier to undergo fractionation, because we have time to produce long-living chambers, and it is much easier that we're going to assimilate part of the crust. We're going to partially melt the crust as well. Okay? So that is why the volcanoes occurring in subduction settings, particularly continental arcs, are the most deadly, because we have magma being generated underneath a thick continent, and if it can undergo differentiation by fractionation and also melting, it can become more silica-rich, more viscous, more gas-saturated, more explosive. Yeah? Whereas if we melt the mantle in a mid-ocean ridge, oh well, we generate oceanic crust. That's fantastic. Or if we're in Hawaii, well, that's a nice plume, but, it's not very deadly. You can take a picture with a lava flow running next to you. So it is different, okay? And if we go into melting of the crust rather than melting of the mantle, then it means we are getting into the metamorphic world. So we're going to leave the mantle and the igneous world to the side, and now we're going to revise metamorphic rocks. So, very different, because we are not producing a rock from crystallizing a melt, like in igneous rocks. We are producing a rock by just recrystallization in solid state. Changing pressure, changing temperature, we recrystallize to become in equilibrium with the new conditions, but without melting. If we melt, we get igneous again. Yeah. So as I said, really, really different composition of granites from basalt, and granites are building most of our continental crusts. Very low iron and magnesium, very high silicon. So we started looking at metamorphism in mid-ocean ridges, actually. Remember that in mid-ocean ridges we have production of melts, and depending on how this melt cool down, we have gabbros, basalts, or pillow basalts. Yeah? This sequence here, from gabbro to sheeted dikes of basalt to pillow basalts, how do we call that? And we see that abducted in places like Oman. Ophiolite, yeah? So what happens in these situations is that we have, in the middle of the ocean, a very toasty environment. It's very hot for being really deep. And so what happens is that water comes through these dikes, gets heated up, and starts metamorphosing our basalts and our gabbros. And the basalts and the gabbros, which are rich in olivine and pyroxenes, are going to start getting hydrated. And those minerals, olivine, pyroxene, don't have water in them. So they're going to start converting into minerals that have water in them, such as serpentine or talc or chlorite. Yeah? We're going to start producing the first metamorphic rocks, the serpentinites, which have lots of these minerals that have still lots of calcium and magnesium and iron, but also water. Yes?
With that image before, with the, like that's an olivine crystals, olivine, the green stuff?
Yes.
So would that be a half, because you were saying that's a residue after a lercellite forms when it forms a basalt?
Okay, that's a good question. A Harzburgite is normally a mantle rock, and these are not mantle rocks anymore. They are coming from crystallization of these basalts. They don't have time to undergo differentiation at all in mid-ocean ridges. It would be more like a cumulative gabbro with lots of olivine. But it's likely that it's going to have also pyroxenes. So if anything, it's going to be a lercellite. Yeah? The Harzburgite would be down here in the region of melting, when you start melting your mantle because you have less pressure. You generate this basalt that comes up, and as a result, you leave a residue which is depleted in CPX. That's the Harzburgite. So that would be somewhere down here. Yeah? You have extracted melt from it, and as a result, you leave the Harzburgite behind. Yeah? Good question. Okay, so if we start hydrating all these mafic rocks, we get the first metamorphic rocks, the serpentinites, with lots of sheet silicates that are able to accumulate water in the structure. And they're also important because when we hit a subduction zone, they're going to be enabling the process because they have all these sheets full of water, and they're going to be good lubricants of the subduction factory. And remember, subduction works thanks to two processes. First, that we have hot material coming out in the mid-ocean ridges, producing tholeiitic basalts. Second, that our hydrated basalts and gabbros are metamorphosing, losing water, and becoming very dense, and therefore pulling the slab down. So all of this process is metamorphism, from very low grade to extremely high grade. What kind of conditions of pressure and temperature do we get here? Extremely high pressure, not so high temperature. Okay? That is the typical conditions we get in subduction zone metamorphism. High pressure, relatively moderate temperature. Yeah? That's a subducting slab and transforming into blistschist and finally eclogite. If we have a more high temperature path, what kind of metamorphism do we get? It's not subduction zone, it is regional or Barrovian or burial metamorphism. And we can also have metamorphism in conditions of very low pressure but increasing temperature. Where does this happen? Contact metamorphism, where we have a volume of magma heating up the country rock. We would also have a fourth type of metamorphism. Remember which one was it? That produces really, really, really high pressure and relatively high temperature, and it's completely out of this diagram. It would be, sorry?
Large impacts on meteors.
Yes, related to impact craters. So you would get really, really extremely high pressure. That would be the fourth one, but we can't plot it here. So these are the three main ones. The fourth one is rare, but really aggressive, let's say. And they occur, as we just discussed, in different tectonic settings. Subduction zone, regional, or contact just and surrounding intrusions of hot magma. Yeah? And we know the way why how the metamorphic rocks undergo these changes in temperature and pressure with time, because we can reconstruct the PTT loops by looking at mineral inclusions, mineral zoning, and reaction textures. Remember that metamorphic rocks are like black boxes. We can look at them and tell apart what happened and why they look like they look. Yep. So an example of frozen-in reactions we saw in the metamorphic rocks was this one. So what is this yellow mineral here? There's one yellow mineral you've looked at. Staurolite, yes. And this is chloritoid, and they are breaking into chlorite green and biotite brown. Both those minerals have much more water than the initial ones. So it would be a prograde or retrograde reaction. If we are making something which is low in water, staurolite and chloritoid become more water rich, is that prograde metamorphism or retrograde metamorphism? Retro, yes. And the way we look at reactions in the metamorphic rocks is by looking at what happens. So when two things react to produce a new one, the new one occurs in the middle. It's the same as we saw between the pyroxene, J-dihydroemphaside, and quartz. They are stable at very high pressure, but when you undergo retrograde metamorphism, they become albite, and that's why you observe albite in between the two. Okay? These retrograde reactions are not as successful as the prograde ones, because the higher the temperature and the pressure you're at, the more enhanced diffusion of chemical elements is, and therefore you are more likely to keep the prograde assemblage, but you are able to see these retrograde reactions coming in by looking carefully under the microscope and looking at these frozen-in reactions. Yeah? And reconstructing the types of pressure, temperature, time loops, or reconstructing the prograde and particularly high grade and retrograde reactions, we can get to know what kind of geodynamic setting we are in. Are we in a subduction zone? Are we in regional metamorphism? Or is it just contact metamorphism? So as we saw, the first ones we looked at was metamorphosing our basalt and gabbro. So we start by producing serpentinites. Those are the very first metamorphic rocks we looked at. They become blue schist when they start undergoing higher pressure, and they start releasing water. And finally, they become eclogite, which is completely anhydrous, dense, and pulls the slab down. And when it pulls the slab down, it mixes with the mantle, and it makes it heterogeneous. And, those are the raisins of the cookie dough. Yeah? And all this water we are releasing is enabling subduction zone volcanism or arc volcanoes, which are going to be generated on top of the subducting slab. Yeah? And we also saw that because the depth at which this happens is critical, depending on the subduction angle, we're going to have the volcanic arc located at different places compared to the trench. The deeper the subduction angle, the closer our arc will be to the trench. In a bit more detail, we have here together subduction zone metamorphism and regional metamorphism, yeah, or boreal metamorphism. So we are in a ocean-continent collision. The oceanic crust or lithosphere, is subducting underneath the continental lithosphere, and we have subduction zone metamorphism here and regional and maybe contact metamorphism here related to this melt production. And the conditions we have with these different numbers are different metamorphic facies. If you remember, these are the names we give to metabasites. So all of the rocks in the subducting slab are obviously going to be metabasites because it's the ophiolite suite, what we are metamorphosing. But in the continent, we will have a different variety of rocks, yeah? We might have gabbros, but we will probably have lots of other things, like sandstones or mudstones or limestones, yeah? So even if we give them different names in terms of metamorphic fascies, when we classify a rock, we only use the terms of the metamorphic fascies for metabasites. That's the convention, let's say. And as I said, in the continent, we may have a variety of rocks. And depending on the rocks we have, we will get a different metamorphic rock as a result. That is the beauty of the protolith. So this is an ACF diagram. Again, don't confuse it with the ternary diagram in the igneous rocks, where aluminium is on top, calcium is on the left, and iron plus magnesium are at the bottom. And all the minerals we've been looking at classify here, excepting quartz and the feldspars. Even if the feldspars have aluminium in them, they don't typically classify here, because we saw that these three minerals are not very diagnostic of metamorphic grade. They just occur everywhere, so it's not very interesting. Whereas these are the ones, plotting here, are going to tell us a lot about metamorphic protolith and metamorphic grade. Okay? So in terms of the protolith, if we are starting with a mudstone, we will get lots of metamorphic minerals rich in aluminium. If we start with a basic igneous rock, we'll get lots of minerals with iron. And if we start with a limestone, we'll get lots of minerals with calcium in them. We start with a sandstone full of quartz, well, we will not get anything. Yeah? We'll just get a quartzite, which would not plot here. Yeah? So the protolith tells us what kind of chemistry we have and what kind of minerals we can generate. The other key thing is the grade, the metamorphic grade. So as we increase grade, the most interesting groups of metamorphic rocks are metabasites and metapelites, because those are the ones that are going to be generating a range of minerals. So in metabasites, we go from hydrated to anhydrous minerals, but all of them have magnesium, iron, and calcium. In metapelites, it's the same story, but the minerals are different because what we have is aluminium. Yeah? And we've looked at these two particularly because they are more interesting. Because if we start with a sandstone, we will just generate quartz, and then quartz, and then quartz, and then quartz. And then we get a quartzite, which is not very diagnostic of metamorphic grade. Yeah? And we finished with having this kind of summary diagram where we have the metamorphic fascist, for example, blue schist, eclogite, green schist, and so forth, which we use to name metabasites. We also have index minerals, chlorite, biotite, garnet, staurolite, sillimanite, kyanite. All of them have aluminium, so we use them to classify metapelites. And we also have the three red lines, which separate the three aluminosilicate polymorphs, andalusite, sillimanite, and kyanite. Yep. And another interesting bit of information is the metamorphic fabrics we get, particularly in metapelites, from slate to phyllite to schist to gneiss, as we increase metamorphic grade. So remember, to name metabasites, fascies. To name metapelites, texture or fabric plus index minerals. Yeah? Naming metamorphic rocks is way easier than naming igneous rocks. It's much more simple. Yeah? And remember also you have to use different textural terms for igneous and metamorphic. And we ended up focusing more in the metapelites because they are really, really interesting in terms of the protolith. So the protolith is a mudstone. And the mudstone basically is kind of the residue of weathering of previous rocks. And as we weather, the first things we're going to get rid of are minerals stable at high temperature, like olivine or anorthite. The last thing we're going to get rid of is aluminium and iron. Our mudstone is going to be very, very rich in aluminium due to weathering, because it's very, very stable under weathering conditions. And therefore, in a mudstone, what we have is lots of clays. Yeah? Kaolinite, smectite, illite, and chlorite all have tons of aluminium. And when we metamorphose a mudstone, we get slates, phyllite, schists, gneiss, and eventually migmatites with a beautiful variety of minerals that tell us a lot of information on the grade. And this is why, to name a metapelite, we use a combination of texture and mineralogy, because both are very indicative of the metamorphic grade we attained in this particular rock. Yeah? And we ended up looking at migmatites last week and in the frac on Monday, where what we get is anatexis, or melting of the crust. This is enabled because we have accumulation of radioactive elements such as potassium, uranium, and thorium, which release heat as they decompose radioactively, and that heat helps us melt the crust. And the melting of the crust, remember, is very, very different from melting of the mantle. First, the temperature. It's kind of half the temperature when we melt the crust than when we melt mantle. And second, the product. Melting the mantle, we get basalt. Melting the crust, we get a granitic melt, let's say. And melting of the crust is enabled because of the accumulation of this radioactive heat-producing elements, and also because throughout metamorphism, and also particularly metamorphism of metapelites, we are releasing water, remember, and water makes melting easy. Yep. So this is the dry solidus, and again, in this diagram here, we can see how the wet solidus shifts to the left towards lower temperatures. So by releasing all this water, we are enabling melting, in this case, of the crust. In migmatite zones, where the melanosome is what we leave behind, the leucosome is the melt we produce, which is very felsic, and the paleosomes are the zones which have not undergone any melting, or the gneissic areas. And the granites we get as a result have very specific chemistry, very rich in aluminium and silicon. Whereas if we are getting granites by just fractional crystallization, we will not be definitely as enriched in aluminium, because the second generation granites, the S-type granites, have come from a source which is a result of weathering and enrichment in aluminium. And to finish, we had this graph where we had the different aluminum saturation groups, peraluminous for S-type granites. I-type granites are typically metaluminous, and the peralkaline ones, where you can see there's lots of alkalis, sodium and potassium, are typically related to fractionation of what kind of melts? Alkaline melts, so hotspot melts, plume melts, okay? And these are the ones you saw for the homework with rubicite, edgerine, and so forth. Okay? Very funny minerals which host all these alkalis that we have excess of. So, now is your turn. I hope you spend time on the subject. Please ask any questions. You have learned a lot in a very short period of time, so I'm very happy. You just need to kind of settle on the information down. It requires time. It requires asking questions and reading. And when you get to the exam, please read the questions and answer accordingly. Bring everything you need, particularly for the practical. Don't forget your drawing equipment and so forth, your hand lens. And best of luck.
I saw this the other day, and I thought you'd like it. So it's a diagram showing a caldera.
That's brilliant.
That'd be fun to do.
Yeah.
You were to do petrology again next year. That would be a fun experiment to do, as well as like you should have done the cooking. You should have had cookies.
First things, and then actually not sure what's exactly is the S9 type. I know the obviously S that come from sedimentary original and I type I know about. But yeah, for example, the practical, for example, this alright, then for example S1, the sample S1, I got a high function quartz, and then there's a little bit less alkalis and then less fragile place. That's what I get. In this case, I just determine because it's granitoid. But Is it S-type because they have a lot of cores? That's what I can
No,
see.
quartz is not the key